What specific problem does your proposed geometry, resource, and domino models aim to address regarding skill dynamics in language models?
The proposed geometry, resource, and domino models aim to address the complex dynamics of skill learning in language models, particularly focusing on the sequential nature of skill acquisition, as exemplified by the domino effect. The geometry model provides a framework to understand how skills are represented and interact within the parameter space, while the resource model interprets skill dynamics through the competition for limited learning resources among tasks. The domino model simplifies this further by assuming a strict hierarchical learning order, where each skill is learned sequentially, only after the previous one has been mastered. Together, these models seek to elucidate the mechanisms underlying the observed learning behaviors, such as sudden jumps or gradual improvements in skill performance, and to provide insights into optimizing training dynamics in neural networks. Ultimately, they aim to bridge the gap between theoretical understanding and practical applications in optimizing language model training.
How does the proposed method or algorithm work? Illustrate step by step the processes in the geometry model leading to the domino effect.
The geometry model operates by making two key assumptions: independence of tasks and linear representation of tasks by model parameters. First, it assumes that the total loss is a weighted average of individual task losses, where each task contributes independently to the overall loss. Second, it posits that each task is represented linearly in the parameter space, allowing skill levels to be determined by their projections onto corresponding task vectors. As the model is trained, the learning dynamics reveal the domino effect, where the second task begins to learn rapidly only after the first task has completed learning. This sequential learning occurs because the gradients of the tasks interact non-linearly during optimization, particularly with optimizers like SignGD, which can cause one task's gradient to dominate and delay the learning of subsequent tasks until the first task's gradient diminishes. Thus, the geometry model captures the intricate dynamics of skill learning, leading to the observed domino effect.
Can you explain the significance of the domino effect observed in your experiments and provide a specific example from your findings that illustrates this effect?
The domino effect observed in our experiments signifies a sequential learning phenomenon where the progress of one skill is contingent upon the completion of another. This effect is particularly evident in the training of two independent sparse parity tasks, where the second task, with a lower frequency, only begins to learn rapidly after the first task has finished learning. For instance, when training these tasks using the SignGD optimizer, we found that the second skill's learning was significantly delayed until the first skill's learning was complete, demonstrating a clear dependency in their learning dynamics. Quantitatively, the time taken to learn the second task was only twice as long after the first task finished, rather than the expected 10 times based on their frequency ratio. This illustrates how skills can compete for learning resources, leading to a structured and sequential learning process, which is a central theme in our proposed models.
What are the theoretical or practical benefits of implementing the resource model compared to traditional methods for training neural networks?
The resource model offers several theoretical and practical benefits over traditional methods for training neural networks. Theoretically, it provides a clear resource interpretation of skill dynamics, illustrating how skills compete for a finite pool of learning resources, which can lead to a better understanding of the sequential learning process observed in tasks. Practically, the resource model simplifies the complexity of the geometry model, allowing for easier analysis and insights into training dynamics without needing to specify intricate details about gradients and task dependencies. Additionally, it can effectively simulate skill dynamics in scenarios where tasks are dependent, making it a versatile tool for modeling various learning scenarios. Finally, the model's ability to tune a single phenomenological parameter, n_0, to match the dynamics of the geometry model across different setups highlights its efficiency and adaptability in real-world applications.
How was the effectiveness of your proposed methods validated in the experiments? What metrics or benchmarks did you employ to measure performance?
The effectiveness of the proposed methods was validated through a series of experiments that focused on training dynamics and skill learning in various setups, particularly using the geometry and resource models. We employed metrics such as the convergence time of tasks, measured by the time taken for a skill to reach a specified loss threshold, and the number of gradient-aligned dimensions throughout training to quantify the domino effect. Additionally, we analyzed the learning curves of different tasks under varying conditions, such as the power law distribution of task frequencies, to observe sequential learning patterns. The experiments included both synthetic tasks, like the multitask sparse parity problem, and real-world applications, such as predicting squared values from inputs, allowing us to assess the model's performance across different scenarios. Finally, we compared the performance of different optimizers, e.g., Atom, Sine GD, to understand their impact on learning dynamics, further validating our models against established benchmarks in the literature.
What limitations did you encounter when applying the resource model, especially in the context of under-parametrization or task correlations?
The resource model encounters significant limitations in the under-parametrized regime, particularly due to the inability to orthogonalize task vectors when the number of tasks exceeds the dimensionality of the model. This leads to inevitable interference among skills, as tasks cannot be represented independently, resulting in non-monotonic dynamics that complicate learning. Additionally, the model's reliance on a correlation matrix to capture task dependencies introduces further complexity, as it must account for both positive and negative correlations between tasks, which can obscure the learning dynamics. The resource model's effectiveness diminishes when tasks are highly interdependent, as it struggles to accurately simulate the dynamics of skill learning under these conditions. Consequently, while the resource model provides a useful framework, its assumptions may not hold in scenarios where task correlations are strong and the model is underparametrized.